Okay, good evening, everyone. Now we are going to start the second day of our chemistry class. So far, we learned about the atomic structure and the evolution of the atomic theory. Right? We learned about the evolution of atomic theory, and under that, we learned about the discovery of the electrons, discovery of the protons, and uh, about the nucleus of the atom. Right? We learned up to the nucleus of the atom. So today we are going to continue from that point onwards. Right. So when we are talking about the nucleus of the atom, so last time I told you that it was given, that means the radioactivity was invented by Henry Becquerel. Right. Radioactivity was invented by Henry Becquerel. That was in 1896. Right. In 1896, he invented radioactivity by an accident. Right. Then Ernest Rutherford, another scientist, he could divide, that means he explained that the radioactivity is composed of three uh, three sub radiations. Those are alpha, beta, and gamma. Right. So those are the things that we are going to study today. Right. So if we have a quick flashback about the things that we learned before, right, about the atomic structure, about the atomic theory of matter. I told you that the atomic theory was first proposed by the Greek philosopher that was Empedocles in nearly 440 BC. So he said that all the material world is made up of four fundamental elements. Those are earth, fire, air, and space. Earth, fire, air, and sorry, not space, water. Then Hindu said that the material world is made up of those four fundamental elements as well as space. Right. Then in around 400 BC, there was a Greek philosopher that was Democritus. He said that Democritus said that the material world is made up of tiny indivisible and invisible particles called atomos. Right. So he named them as atomos. But Aristotle uh, he formulated the notion that there are no ultimately tiny indivisible particles. So therefore, uh, the atomic theory, it was faded away for many centuries. Right? It was faded away for many centuries because of the Aristotle's what we call statements. Right. So therefore, uh, it was back in 1808, John Dalton, right, an English scientist as well as school teacher, he proposed that atoms are made up of, that means the material world is made up of atoms, which are tiny indivisible and invisible particles. And he came up with four postulates for that. So we talked about those postulates and all those things. Right. Then I'm not going to remind these postulates again because we have already learned about those things on that day, on the first day. Right. So then it was the time that people invented subatomic particles. Right. It was Johnston G. Stoney. He gave the name electron to the fundamental current carrying particle. And then J.J. Thomson proved the presence of electron using his experiment using a hollow anode. So he could prove the presence of these. Then That was the discovery of the electron. That was by J.J. Thomson. So the golf ball model proposed by Dalton was disproved by Thomson, and he put forward the plum pudding model, right? And then he gave that cathode rays are having properties, and those properties we discussed on that day, right? Then we talked about the applications of the cathode rays as well, and it was in 1909. Robert Millikan, he conducted his oil drop experiment, and he was able to find out the charge of an electron as 1.602 into 10 to the power minus 19 coulombs, right? That was Robert Millikan. It was in 1909. Then with that, before that, Thomson was able to find out the E over M ratio, right? So he found E over M ratio as 1.76 into 10 to the power 8 coulombs per gram. And with the discovery of the charge of an electron by Millikan as 1.602 into 10 to the power minus 19 coulombs, he was able to find out the mass of an electron as 9.10 into 10 to the power minus 28 grams. Right. So that was a discovery of the mass of the electron. That was by Millikan. Right. So then we talked about the nucleus of the atom. Right. We talked about the discovery of the nucleus of the atom. That was by Eugen Goldstein. He did an experiment using a perforated cathode. Right. He did an experiment using a perforated cathode, and with the help of that, he could prove the presence of the positive particles, right? That's what we call positive rays, and with that, scientists started to believe that there should be some other amount of subatomic particles, those subatomic particles, they are composed of positive charges, and then they name them as protons, right? They named them as protons, right? So that was the invention of the proton. But Goldstein could not prove the presence of a proton, right? Goldstein, he could not prove the presence of a proton, but he predicted about that. Then the positive rays, or the canal rays, they named them as canal rays, right? They too were said to be having properties, right? Like the cathode rays, they were said to be having the property that they travel in straight lines. They possess a mass and kinetic energy. They are positively charged. The cathode rays are negatively charged, but these positive rays, they are positively charged. And not like the cathode rays, they depend on the type of the gas that is taken into the discharge tube. Right? Right. They depend on the type of the gas. Then with that thing, they found that the mass of a proton was 1,840 times the mass of an electron, right? And then they believed that these protons must be another subatomic particle, because they showed some common properties, and they were varying from gas to gas that they use. But those variations were perfect multiples of the smallest positive particle that was given by hydrogen. Usually hydrogen was given the smallest positive particle with the lowest mass, but all the others, they were given the multiples of that mass. Okay, is it clear? Right. Then that is a summary of the thing that we learned in our previous class. So then let's continue from that point onwards. Now today we have to talk about the radioactivity and the other stuff. and the invention of these other subatomic particles. Right. So get ready to get the notes and prepare for the lesson. You can write the topic today, that is radioactivity. Right. The topic today is radioactivity. Okay, now let's see what is meant by radioactivity. Now radioactivity, it was invented by the French scientist Henri Becquerel. Right. So there was a French scientist called Henri Becquerel. He was a scientist. Uh, Henri Becquerel. He was a scientist who invented radioactivity in 1896. Right. He invented radioactivity in 1896. Right. So actually, this was an accident. It was an accident made by Becquerel. That means he was dealing with some elements. By that time, scientists were so keen to discover new elements. So Becquerel was also working on inventing a new element. So one day, at the end of his work, he put one of his samples in a drawer and went home. And on the following day, once he came, he observed that there were some photographic films that were in the drawer, and they are having some marks. Those photographic films are having some marks. Those are given from some strange marks. So he could not find any source of light to give those marks in the photographic films. So therefore, he thought that there should be something that is coming out from the sample that he was working with. So that must be some sort of radiation. So therefore, he named those particles as radioactive particles. So that was a discovery of the radioactivity by Henry Becquerel. Right. Then there was another scientist called Lord Ernest Rutherford. Right. Lord Ernest Rutherford, he did further experiments with radioactive samples, and he found out that there are three types of radioactive particles. Those are alpha, beta, and gamma. Right. So then he named them as alpha, the symbol is this one, beta, symbol is this Greek letter beta, and gamma. So Rutherford began to work with these radioactive samples, right? And he worked with these radiations, and he was able to characterize some features of the atom using these radioactive uh, samples, right? So what he did was he placed a radioactive sample on a lead block. Sorry. he bore a hole on a lead block like this and then placed those radioactive sample on the lead block. Okay, now this is the lead block. Then he placed the radioactive sample over here. And then he placed an electric field like this, and then started observing the radiations that are coming out of this. And he also placed a photographic film on the other end as well. Right. So there we have radioactive substance, and then he observed the radiations that are coming out from this. He saw that some rays are coming from the radioactive source and they are going towards the photographic film undeflected, right? So they are going towards this film undeflected like this. That means without any effect from the electric field. Then he also observed that there are some rays which are deflected greatly towards the positive plate. And he also observed that there are some rays which are deflected slightly towards the negative plate. Then he named those as alpha rays. Alpha rays, beta rays, and here we have gamma rays. Right. So that is how he uh, got the observations. Then with this observation, he suspected that the beta rays must be having a light weight. That's why they are deflecting more in an electric field. Then gamma rays should not be charged. That's why they are not deflected, undeflected. And alpha rays, they must be having a higher mass and positive charge. That's why they are deflecting towards the negative plate of the electric field, as well as they are deflecting only slightly. Right. So that's what he was able to predict. Right. Then with the help of those observations, he named them as alpha, beta, and gamma rays. Right. So let's move on with this one. Write the topic today, radioactivity, and let's go to the note. That means let's write a small note. And I think you all have written the topic. Right. You can write down. With the discovery of the radioactivity, with the discovery of the radioactivity by Henry Becquerel, with the discovery of the radioactivity by Henry Becquerel in 1896, in 1896, The British physicist, Lord Ernest Rutherford, showed that radioactive materials produce three types of emissions. Those are alpha, beta, and gamma. Right. So you can say he also showed that alpha particles are right. He also showed that alpha particles or alpha rays consist of positively charged particles uh, positive charged particles called alpha particles Therefore, they are deflected towards the negatively charged plate of an electric field. Therefore, they are deflected towards a negatively charged plate of an electric field. He also showed that beta particles or beta rays show the identity of electrons so that they are deflected towards the positively charged plate the positively charged plate of an electric field. Then you can say the third type of radiation. Oh, third type of yeah, you can write down third type of radiation consists of third type of radiation consists of high energy rays called gamma rays. High energy rays called gamma rays. They are not affected by an electric field. They are not affected by an electric field or magnetic field. They are not affected by an electric field or magnetic field as they are uncharged. Right. So you can sketch this diagram. Right. So this is what Rutherford did to identify the characters of alpha, beta, and gamma rays. Okay. Quickly draw this diagram. Draw this diagram quickly. I'll give you a couple of minutes. Right. So then let's move on. I think the time is enough to draw this. Okay. Finalize your drawing. I'll give another minute. Right. The time is enough, I guess. Right. Now we are going to learn about another experiment conducted by Rutherford. We call it Rutherford's gold foil experiment. Right. That means Rutherford, he developed this experiment and he placed a thin foil of a metal on the path of the rays, on the path of the alpha rays. Actually, he used a source of alpha radiation and he placed a thin metal plate which is made up of that means gold, steel, likewise different metals he used. But he succeeded in getting some observations once he used gold. Right, he got some observations from the other metals as well, but he succeeded in getting measurements once he used gold. Right. What he did was, what he did there was like this. Let's say, let's try the topic Rutherford's gold foil experiment. Right. Rutherford's gold foil experiment. Now Rutherford, together with his associate Johannes Hans Wilhelm Geiger, he was the associate, and by that time there was another German, uh, not a physicist, actually a university student. We call them undergraduates, called Ernest Marsden. So with the help of those two scientists as well, Rutherford carried out a series of experiments using very thin foils of metals as the targets of alpha radiation source. So then he succeeded in measuring, not measuring, he succeeded in getting observations once he used gold foil. Right. So what he did was a thing like this. He placed a radioactive source in a lead block. Right. So this is the lead block. He placed the radioactive source. Actually, he used an alpha radiation source. Then he placed a thin gold foil like this, and surrounding it, he placed a circular fluorescent screen. He placed a circular fluorescent screen like this. Then once he irradiated the gold foil with this alpha radiation source, he got observation that these majority of these rays, they are traveling undeflected, right? Majority of the rays are traveling undeflected, passing through the gold foil. Then small amount of radiations, they are traveling somewhat deflected, not greatly, they are deflecting to some extent, like this. And he also observed that a very rare amount of radiations, they are deflecting back. The majority, it passes undeflected, a very rare amount deflected slightly, and extremely small amount deflected back. So those are the observations that he got from this experiment. Then to explain these observations, right, to explain these observations, he said that the most of the space in the atom must be empty, right? he said that most of the space in the atom must be empty, right? And there should be a dense nucleus in the center of the atom, right? Which should be a bunch of positively charged particles. It should be a bunch of positive charged particles, and all the other space is empty, right? So this was the experiment conducted by Rutherford. So let's write about this one. You can write the subtopic: Rutherford's gold foil experiment. Rutherford's gold foil experiment. Okay. You can write down: in the period of 1908 to 1909, in the period of 1908 to 1909, Lord Ernest Rutherford carried out a series of experiments together with Johannes Hans Wilhelm Geiger. Together with Johannes Hans Wilhelm Geiger and Ernest Marsden. In the period of 1808 to 1809, Lord Ernest Rutherford, together with Johannes Hans Wilhelm Geiger and Ernest Marsden, carried out a series of experiments using very thin foils of metals as the targets for alpha particles. As the target for alpha particles. There he observed that not here, you can write there, they observed that most of the alpha particles are traveling undeflected comma A small amount of alpha particles are deflected slightly and very trace amount of alpha particles are bounced back in the direction from which it came. Right. Now let's draw this diagram. This is a rough sketch of the experiment conducted by Rutherford. Now here we have a lead block. I forgot to ask, what's the reason for using lead block? Because lead can stop the radiations. So that means if we have a small hole over here, the alpha particles are coming out only from that hole. That means the alpha particles will not be traveled to the other directions. Lead can stop the radiation. Right. Draw this diagram quickly. Right, I think the time is enough for you to draw this diagram. Okay, so let's move on. To explain the results of this experiment, Rutherford devised a new model. To explain the results of this experiment, Rutherford devised a new model for the atomic structure Rutherford devised a new model for the atomic structure, suggesting that most of the space in the atom must be empty. Most of the space in the atom must be empty. There is a reason for most of the alpha particles to pass through the gold foil with little or no deflection. Pass through the gold foil with little or no deflection. Then in a new point you can write down. They also suggested that all the positive charges of the atom all the positive charges of the atom are concentrated in the nucleus where alpha particles experience a large repulsive force. Alpha particles experience a large repulsive force. Therefore, they show a greater deflection. Therefore, they show a greater deflection. And you can say, moreover, when alpha particles travel directly towards the nucleus, they would experience an enormous repulsion. Enormous repulsion. That it could completely reverse the direction of the moving particle. All right. So those are the observations and how he explained this one. So with this thing, he came up with a new model of the atom. He said that in an atom, there's a dense nucleus at the center. So when alpha particles come They are traveling undeflected like this without any issue. See, the majority of the alpha particles, they travel without any issue. But when an alpha particle, I'll use a separate color. If an alpha particle comes towards the nucleus, they will experience a greater repulsion and then they are deflected. Right? So it will be deflected like this. Because the alpha particles are also positive, the nucleus is positive, therefore they are showing a deflection. If that particle is coming directly towards the nucleus like this, then it is bounced back to the direction which it comes from. Now see, since most of the atom is empty, most of the particles, most of the alpha particles are traveling undeflected without any obstacle. But there's a small part where the positive particles are stuck together. As a result, there will be few deflections taking place. Right. So based on this, Rutherford gave a new model for the atom that is called the Rutherford's model. He gave that model in 1911. Right. He conducted his experiment in 1908 to 1909. Then he gave a new model for the atom. Right. So you can draw this diagram. This is the deflection of the alpha rays. Now draw this diagram quickly. Right. I think the time is enough for this one. Okay. In a new point, you can write down. Based on those observations, Rutherford gave the planetary model of the atom. Rutherford gave the planetary model of the atom, stating that the protons are packed at the nucleus and electrons are scattered around it like planets around the sun. Right. So this is the Rutherford's model. Right. He said that there is a dense nucleus and the electrons are scattered around it randomly like this. Right. So this was the Rutherford's model proposed in 1911. These are the electrons. Here we get the nucleus. So this is called the Rutherford model, which was proposed in 1911. Right. You can draw it. Right. So that was the discovery of the new subatomic particle proton. Draw this quickly. Right. I think you have finished drawing. So let's move on. You can write down subsequent studies based on mass spectroscopy revealed that the masses of atoms were revealed that the masses of atoms were much greater than the sum of the protons and electrons present in it. Right. Therefore, they suspected of the presence of Therefore, they suspected the presence of another subatomic particle which has no charge, another subatomic particle which has no charge, but with a mass which contribute towards the atomic mass. Right. Then you can say based on this idea, Sir James Chadwick in 1932 right. Sir James Chadwick in 1932 discovered the presence of neutron neutron spelling is neutron neutron comma another subatomic particle which has a zero charge and a mass nearly equal to the mass of a proton. Right. So the mass of a neutron, it was found to be 1.6749 into 10 to the power minus 24 grams. Right. So let's write those values as well, because those values will be coming in the, that means you will be tested for those values in the exam. So he invented neutron. So the mass of the neutron was found to be 1.6749 into 10 to the power minus 24 grams, or we can give it in unified atomic mass units, that is 1.008665. So this is the mass. Right. So that's the mass of neutron. Right. So with these things, there was another scientist called Niels Bohr, right? Niels Henrik David Bohr, a Denmark scientist. So he collected all the ideas back then. Back that was in 1913, but right. This was before the discovery of neutron even. Right. He collected all these. He combined all these ideas about the atom back then, and he came up with uh, a new, not a new actually, a modified model for the atom. He modified the model given by Rutherford, and he came up with uh, what we call Rutherford Bohr model of the atom, or we simply call it Bohr model of the atom. Right. So let's write down. In 1913, Niels Bohr His long name is Niels Henrik David Bohr, but Niels Bohr is enough. In 1913, Niels Bohr combined the ideas about the atom then and postulated a new model explaining that electrons are placed in fixed orbitals stating that electrons are placed in orbitals like planets around the sun. Right, so let's write down the model. Sorry, let's draw the model. Now Niels Bohr, he stated this one, and he said that there's a dense nucleus at the center, and around this nucleus there are orbits. Like this. In each of these orbits, there will be electrons. Like this. So those are the electrons. And here we have the nucleus. And this is called the Bohr model or the Rutherford-Bohr model. The Bohr model of the atom. Okay, draw it quickly. Right. So this is the Rutherford Bohr model. Then below this you can write down the particles which are found in the nucleus right. You can write down the particles found in the nucleus are called nucleons. Particles found in the nucleus are called nucleons. Within brackets, protons or neutrons. Protons or neutrons. Right. Then you can write down right. Next point you can write down the nucleus of an atom. The nucleus of an atom that has specific numbers of protons and neutrons that has protons and neutrons is called a nuclide. Nuclide. Right. It is called a nuclide. Now, all the protons and neutrons are called commonly as nucleons, and a nucleus with all the nucleons is called a nuclide. All right. Now the time is 9:40. Now it's our time to take the break, short break, and after the break, let's meet again to talk about the atomic number, isotopes, and the mass number. Right now, all the history parts are over now. Now we are going to move on to the calculations, and let's take a 15-minute break, and we will be meeting again at 9:55 to discuss these things. Right. Don't quit the meeting. Stay connected. Right. Right. So welcome back after the break. Now we are going to talk about the atomic mass and the other concepts. Right. Now we learned about the atomic theory and the evolution of the atomic theory so far. Right. Now, based on these discoveries, scientists they found out that there are different combinations. Actually, there are some relationships between these atomic masses and the things. Right. There was a scientist called Moseley. His long name is Henry Gwen Jeffrey Moseley. Right. Uh, he was an English physicist, and he also worked with Rutherford. Actually, we can say he's a co-worker of Rutherford. He found out that the number of positive charges, on the nucleus increases in atoms by single electron units. It increases by single electron units. So that was his discovery. So then again he showed that the atoms of each element have a characteristic number of protons. They have a characteristic number of protons, and the number of protons in an atom of any particular element is called the element's atomic number. So he was the one, that means Moseley is the one Moseley is the person who invented this atomic number concept. Okay, so let's write down the subtopic, atomic number. Right, atomic number. You can write down Henry Moseley. Okay, I'll write the spellings. Henry, I'll write the long name. Henry Gwynne Jeffrey Moseley. Henry Gwynne Jeffrey Moseley found that the number of positive charges on the nucleus found that the number of positive charges on the nucleus increases in atoms increases in atoms by single electron units. By single electron units. Right. Then you can write down the atoms of each element the atoms of each element have a characteristic number of protons have a characteristic number of protons right. The atoms of each element have characteristic number of protons, right. Then you can say the number of protons in an atom the number of protons in an atom the number of protons in an atom of any particular element is called that element's atomic number. Is called element's atomic number. Right. The atomic number is symbolized by capital Z. Right. Capital Z. Now we can say atomic number equals to number of protons in the nucleus and also it is equals to number of electrons in the atom. Number of protons in the nucleus equals to number of electrons in the atom. That is the relationship. Right. Now we know that the atoms are neutral. That means atoms have no charges. They are electrically neutral. Therefore, the number of electrons it contains is equal to the number of protons found in the nucleus. The number of electrons that contain is equal to the number of protons found in the nucleus. Right, let's write down. Right, you can write down. Since an atom has no net electrical charge, since an atom has no net electrical charge, the number of protons is equal to number of electrons, number of protons is equal to number of electrons. Right. Now, for example, if we consider carbon atom has 6 protons and 6 electrons. Right. If we consider oxygen atom has 8 protons and 8 electrons. Likewise. Right. But they found out that, right, in the same time, they found out that the mass of the, mass of the atom is somewhat different than that of the mass of the protons in it. Right. So then they thought of that there should be another subatomic particle. So J.J. Thomson, along with another scientist called William Aston, they used an equipment called mass spectrometer. Right. They used it in 1912 to 1913 and discovered the first ever isotopes of neon. Right. So that was a discovery of the isotope. So with that thing, they gave the idea that there should be another subatomic particle which has a mass which contributes towards the mass of an atom, right? So then they said that the number of protons plus number of neutrons, that means the mass of the nuclide, is equal to the mass number, right? So that was a discovery of the mass number. Okay, write the subtopic mass number. That is capital A. You can write down J.J. Thomson and William Aston. J.J. Thomson and William Aston were able to discover J.J. Thomson and William Aston were able to discover the first isotope of neon. Were able to discover the first isotope of neon using mass spectrometer. Using mass spectrometer. They found that atoms of a given element can differ in the number of neutrons they contain. So their mass can also vary. Right. Then you can say in a new point, the number of protons plus neutrons the number of protons plus neutrons in an atom is called mass number. Mass number capital A equals to number of protons plus number of neutrons. Number of protons is as atomic number plus number of neutrons. Okay, you can write it. Right. Then that is the mass number relationship. Okay. In any point you can write down the atomic number and mass number. The atomic number and mass number atomic number and mass number can be represented in the atomic symbol as follows. Right. It's like this. Let's say an example. Let's take the carbon as example. Here we can write it like this. The atomic number is given on the left bottom of the symbol, and mass number is represented on top left of the atomic symbol. Here we have the atomic symbol. So this is the standard way of representing atomic symbol. Okay, you can write the example. Right. Now let's move on. Now we are going to learn about the isotopes. Try the subtopic isotopes. Right. Isotopes are the atoms of the same element with same number of protons but different number of neutrons. Right. Let's try the definition. Atoms with identical atomic numbers atoms with identical atomic numbers but different mass numbers atoms with different atomic numbers atoms with identical atomic numbers but different mass numbers are called isotopes of one another. Right. Are called isotopes of one another. Right. You can write down, for example, carbon. Carbon has carbon 12. Now this has 6 protons, 6 electrons, and the number of neutrons is also 6 because mass number is the number of protons plus number of neutrons. Let's see another one. Chlorine. Sorry. Carbon has carbon 13. It has 6 protons, atomic number is 6, 6 electrons, but the number of neutrons is 7. That's why the mass number becomes 30. Number of protons is 6, number of electrons is 6, and number of neutrons is 8. Right, have you finished writing? Right, so that is about carbon isotopes. Right, so let's see another one. Chlorine. Chlorine has chlorine 35 and chlorine 37. It has 17 protons, 17 electrons, and the number of neutrons here will be then 18. Here also 17 protons, 17 electrons. Number of neutrons will be 20. See? Right. So here number of neutrons is the one that is changing. See? All the others are the same, but the number of neutrons will be changing. Right. I think you have finished writing. Right. You can write down isotopes of an element isotopes of an element which are stable in nature isotopes of an element which are stable in nature are called stable isotopes are called stable isotopes and those are not stable and those are not stable are called radioisotopes. Right. So they are called radioisotopes. All right. Now we are going to learn about the atomic mass scale. Okay, write the subtopic atomic mass scale. Right now, we know that atoms are very tiny masses. Atoms are very tiny masses, so therefore we can't use the conventional units like grams, kilograms, and other things to measure out these masses. The reason is atoms are tiny masses. However, scientists have defined a new unit that is called Unified Atomic Mass Unit, simple U, to deal with these extremely small masses. Right? 1 U, that means atomic mass scale is given in U. Right? 1 U is defined as 1 Dalton. I gave it earlier as well. Right? That is defined as 1/12 the mass of a carbon 12 atom. 1/12 into mass of a carbon 12 isotope. That's how we define the atomic mass unit. Okay, write the subtopic atomic mass unit, sorry, atomic mass scale. Right, you can write down. Atoms are very tiny masses. Therefore, atoms are very tiny masses. Therefore, it is it is not convenient atoms are very tiny masses, and it is not convenient to use conventional units like it is not convenient to use the conventional units like grams and kilograms. grams and kilograms to measure the atomic masses. Therefore, a new unit that is atomic mass unit. Therefore, a new unit that is atomic mass unit within bracket simple U to define the masses of atoms. Right. Now you can write the relationship over here. 1U equals to 1 Dalton and 1U equals to 112, the mass of carbon-12 isotope. Right. So let's move on. Now this can be given as unified atomic mass is defined as a mass of exactly 1/12 of a chemically unbound carbon-12 atom. Now 1 mole of carbon-12 atoms is equal to 12 grams. So therefore, we can explain this one. This is how we are going to explain this. One U equals to 112 into 1 mole equals to 12 grams. So we can divide it by the Avogadro number. Once you simplify, you will get this in grams, that is 1.66054 into 10 to the power minus 24 grams. right? So that is the value of 1u. Then opposite of this one, we can say 1 gram equals to 1 divided by this value. Right. So that is 6.02214 into 10 to the power 23u. So those are the relationships between these atomic mass units and grams. Okay, write this down. That finished. Right. Then let's talk about the average atomic mass and the relative atomic mass of an element. Average atomic mass and relative atomic mass. Write the topic. Right. So let's move on. Most elements occur in nature in the form of isotopes. In the form of isotopes. Therefore, the mass of an atom can be expressed as relative atomic mass or atomic mass. Average atomic mass or relative atomic mass can be given as the summation of the isotope mass into fractional abundance. So that is how we express this one. Right. Write this down. Right. Then you can write down when the atomic mass is expressed as moles of atoms, is expressed as mass per mole of atoms. Is expressed as mass per mole of atoms. It is called molar mass of the it is called the molar mass of the element or atom. Right, so it is called the mass or the molar mass of this one. Right, so let's see. I'll see an example. You can write down this question. A sample of chlorine has 75% chlorine 35 isotope and 25% chlorine 17 isotope, chlorine 37 isotope. Calculate calculate the relative atomic mass or average atomic mass. Right. I'll give you a couple of minutes to do this. Right, your time is up. Now let's see how to do this one. Now we can use the equation average atomic mass equals to summation of isotope mass into fractional abundance. If it is so, we can say average atomic mass it is equals to the fractional abundance of chlorine 35 will be 75%. 75% means 75 over 100 and its mass is 35. And then we have 37 isotope and it has an abundance of 25. Right. So once you simplify this one, you will get an answer as 35.5. So the average atomic mass of chlorine isotope chlorine is 35.5. Right. So that's how we find it. Right. So in that manner, we can find out the atomic mass. All right. So with that thing, now our time is up, and we will be ending the class for the day, and we will be meeting on next day to discuss the rest of this lesson. There we are going to talk about the formation of ions and the other things during this lesson. Right. So then, if you have any doubts, you can ask me. If not, we can end the class over here.